go. So, welcome everybody. Welcome everybody to this January edition of Cloud Native Asturias. This is the January 21 event. Thank you very much for coming along. I hope you enjoy this time with us. That's the main goal that we have here. And today I believe that we have two amazing speakers with great content, I can tell you, really, really interesting. Angel, how are you, man?
I'm really good, thanks. I would like to thank everybody for attending this second session of Cloud Native Asturias. We are super happy to have you with us. And yeah, I'll give it back to you so that you can introduce the speakers of today, which is they bring very interesting talks indeed.
I'm very excited, actually. I'm very excited. So yes, welcome. As I mentioned, this is an official CNCF community group, Cloud Native Asturias, as I mentioned before. This is our motto, this is our motivation, or vision, let's say, elevating Asturian technological landscape through the worldwide collaboration. And that's why we believe we need everybody in this trip. Okay, we have people from Asturias, people from outside Asturias, as you can see in the session today. So this is amazing. Since this is an official CNCF community group and event, we will follow the code of conduct of this community. Of course, this is nothing very strange, so just be nice, try to not offend everybody, because that's against of the code of conduct. Okay. As usual, you can follow us in the social media. During the session of the speakers, we will try to share screenshots, comments. You can follow that in that hashtag that we have, Cloud Native Asturias, and since this is taken from January, CNA Jan'21, okay? Okay, this is the agenda. I will try to shut up as soon as possible, and then I will follow with Víctor, Prow ChatOps for open source, and afterwards with Rafael, that I will introduce right now, architectural caching patterns for Kubernetes. So the first speaker, as I mentioned before, Víctor. Víctor is from Asturias, from Spain. Víctor is working as DevOps platform in Idealista. Maybe you know Idealista is a very important company that delivers, I would say, one of the most important platforms in terms of searching for apartments and houses. Actually, I can tell you that it's a good tool. He's especially interested in container orchestration and automation processes. Thank you very much, by the way, Victor, for coming along. And after that, the session from about architectural caching patterns for Kubernetes, we have Rafael. This is a privilege to have you here, man. He's integration team lead at Hazelcast. He has a book, Continuous Delivery with Docker and Jenkins, trainer, conference speakers, and as you can see here on the screen, he worked in very important companies such as Google and SER. So, said that, a reminder, during the whole session, you can see in the right side of the screen a special place to chat. You can chat with us, with everybody, and also you have a special tab, which is for the Q&A. Okay, I encourage you guys to everybody, girls and guys, to put all your questions over there. Okay, we'll get all of them, and we will provide that questions to the speakers at the end of each session. So, last but not least, if you are interested to participate as a speaker in some of the sessions that will come, I can tell you we will try to make a monthly basis event. You can go to this link. You can take it with your phone, and you will access the web form to fill it and provide your proposal. So that's it from my side. And now I will stop sharing, and I will leave the stage to Víctor. Víctor, all yours.
Hi, do you listen to me?
Yes, perfect.
So we are ready to go. Okay, let me share screen. Okay, so we start. Well, hi, and thanks to the community for having me as a speaker in this Cloud Native group. This story starts a few months ago when I tried to start committing and contributing to the Kubernetes project. And as you should do, you should learn and study a bit about the contribution process on the pull request system. And the result of that is that instead of contributing to Kubernetes, I started contributing to the system that makes the continuous integration for Kubernetes, which is Prow. So that's what we are seeing today. The agenda is very simple. It's what is Prow. We'll see also a big picture of the architecture of Prow itself. And we'll see an example of a pull request being pipelined through this process of continuous integration of delivery for the Prow system. Also, we learn a bit about how to set up the Prow instance in any cluster that we have set up. So, with big question, what's Prow? Well, years ago, Kubernetes developers in the community were having a lot of issues with Jenkins, which was the platform that they used to make the continuous integration, because they have to deal a lot with restarts. Also, they were scaling a lot in community contributions, so the problem is also escalate. So they put themselves together and said, okay, we need to develop some sort of system that scales very well. And we all come from different backgrounds, and we know very different languages and tech stuff, but we do know a lot of things about something, which is Kubernetes. So yeah, they did a Kubernetes-based continuous integration and delivery system. And the big feature about this is that every component in the architecture of this system is based on Kubernetes components such as deployments, config maps, secrets, and pods. Indeed, every build process or job that you want to run in this system is run as a pod instance inside the cluster. This also solves the problem that they had with Jenkins, that it was a stateful system, because now as a Kubernetes system, they are fully declarative. And so they have every single piece of code inside a YAML manifest that they can reapply at any given time. So they have infrastructure as code for this system. Also, it provides a lot of information through a web user interface and that have metrics and awesome stuff. And also they expose a Prometheus exportive with metrics that you can scrape if you are into that. So the big feature for me of this Prow system is batch merging of pull requests. In traditional systems or traditional process for continuous integration, you may have your main branch and you open some pull requests that are targeting that branch. These commits are tested against the head of the branch, and if they pass the build, you hopefully merge this PR. However, if you merge the PR, you need to update and retest all the tests for your PRs, because you want to test against the latest head of the branch, not an outdated one, in case you may have any Git conflict. As you may notice, this scales very poorly if you have a community that is growing a lot, like Kubernetes, Prometheus, Istio, Knative, etc. So what the solution that they propose is that they have some PRs that are passing the test. They place these commits all together inside a merge pool. They test the PRs against each other and against the head of the branch. And if the tests succeed, they will merge all the commits all together. Of course, if you want to, you can configure the method for this merge. You can merge, like always, you can rebase, and you also can squash. So the next time a PR is submitted, it will wait for the next merge pool. It will be inserted in the merge pool, and then it will be merged to the main branch again. Also, this system is fully automated by comments in pull request in GitHub. So you can type / and any command, and the bot will take an action based on it, like putting the looks good to me, or okay to test, or whatever tag you have for the pull request. The bot will tag as you comment. And also it will welcome and give extra information for your pull request. It will also suggest some approvers and reviewers for your pull request, which is very useful for a community project because you want to have an approachable community because you want more contributors to your project, obviously. Also, you can honk other people because, well, the functionality of these commands is made by the community, and there is also a functionality which, as internet people, we all love cats, so you can send cats to people. Also, a cool feature is per director reviewers and approvers. Prow supports a file which is the owner's file that you can place in each single directory, and it is very useful because when you have a project that scales and have a large tree directory, you simply cannot know what happens in every single piece of code. So with this owner's files per directory, you have the appropriate user for each piece of code. And indeed, when you open a PR, the Prow system will look at these owner's files and suggest some approvers and reviewers. We'll talk more about approvers and reviewers later on. And how does this all comes together into the Kubernetes system? Because we need to run our builds and our jobs, and these jobs are run as Kubernetes objects. So what the community that creates is a custom resource definition for Kubernetes, which is quite the standard definition for any objects in Kubernetes. You can see it has an API version, a kind, and metadata, and specs. And the important part about the specs in this custom resource definition of a Prow job is that it contains a pod spec, which are the specs for the pod that will be run the Prow job. And also it will contain information about the Git environment, like target branch, commit for the pull request, and a bit information about the author. So now that we have seen the main element of the system, which are Prow jobs, we'll see now how this component interact with the whole architecture. This is the big picture. Every single piece every single component in this diagram is represented in the cluster as deployments or config maps, etc. So it's pretty awesome. So let's see component per component. First, we'll begin with hook, which is probably the most important component in the whole Prow system. Is the component that is constantly listening to GitHub webhooks. And it will parse each webhook that it receives, and depending on the information and metadata that it has, it will route this webhook to a corresponding plugin. Plugins are developed by the community. Anyone can develop and plug in a plugin, obviously, to Prow. And these plugins are the ones that implements the current behaviors for the Prow bot that answers pull request and comments on your pull request and make every interaction. So they are responsible for labeling your PR with the number of lines that you are committing or suggest or approvers, or even creating the Prow jobs. So next component is Plank. Plank is some kind of Kubernetes operator. It will be constantly, I think every 2 minutes, iterating through the Prow jobs that are in the system, and depending on the state of these Prow jobs, they will take an action. They may create the pods for running your builds, or they may just notify back the results of a build to the GitHub status checks. Next component is Tight, which is the component responsible for merging those PRs in batches, like I mentioned before, and also the component responsible for retesting. Deck is an also component that you can use whenever you want to check the status of your jobs. You can have an historical of your jobs and of your pull request. Sorry, you may have also a historical of your jobs, and which are not the same as pull request. You can define a Prow jobs that are run for every single PR, and you will have an historical of those jobs and also the historic of your PR. And then you may have and historical for the tight integration system. Last but not least, there are 3 small other components. Orologium, which is a component, some kind of cron scheduler that will create pro jobs based on a schedule. Sidecar, that is a garbage collector, but for Kubernetes resources like pods or config maps, logs in containers, etc. And Crier, that will send notification to Slacks or public subscribe systems. So let's see how this works together in a real PR process. First thing, you need to open a PR. It's very simple. We all know how to do this. Then GitHub will send a webhook to our hook component, which will have an ingress. And this hook will process or will trigger some plugins that are in charge of labeling our PR. There is an interesting plugin that, apart from suggesting your approvers and reviewers based on the owner's file, it will also count the lines of code that you have modified. So it will add a label with XL or large or whatever your pull request size is. So it's better for the reviewers to schedule their times. At this point, no plugin have created the pro job in the system. In order to do that, our valid reviewers from the owner's files must comment on your PR with the /awk2test command. This is implemented in order to have a gate with the world, because as you are a community which is open source and everything, all that, you may also have trolls and people that are just spamming your CI system. When this comment is commented in your PR, a special plugin called Trigger will create the pro job object in your Kubernetes cluster, and eventually a blank component will have a look at this PR, at this pro job, and will generate the pod that will run the build and then notify the results to your GitHub status of the pull request. Then this is again not enough for having your pull request merge into the main branch of the Kubernetes or whatever project you have. An approver may need to comment your pull request with the command /approve. This is because mainly you may need to have, I don't know, a milestone or a feature that should be checked tightly. And that's what the approver does. And then when it have the approve label, it just is tied will just merge the PR. So if you want to know more about this process, when the slides are made public, you have these 2 interesting links, which are an article from the community, which is in the GitHub repository of Life of the Project, which is awesome, and also a sequence diagram, which is drawing UML, and it shows every single piece of interaction that is made in the system during the process of a pull request. So last part is how to set up Pro in any repository. You may notice that I put the GitHub logo here, and it's not coincidence. Pro is only intended to work for GitHub, or at least at this moment. There are open issues to work on other platforms like Bitbucket or GitLab. However, they are not being developed. They are just being discussed. So as this is a community-driven project, you may want to take on those requests by yourself. I don't know. Pull requests are open for you. So it's very easy to set up a Pro instance in a running Kubernetes cluster. What you need to do is obviously create a GitHub account that will be used by the bot to comment on your PRs, do the merges and all those sorts of things. And you also need to create the personal access token for this bot. Notice that this bot and this personal access token should have access to the repositories that you are wanting to observe. Also, at this point, you need to fork the repository Kubernetes/test infra, which is the repository which is hosting the Prow project. And of course, you need to fork it because you want your infrastructure as code for your organization. Well, as Kubernetes Prow instance is hosted in Google Cloud Platform, it's very easy to set up in Google Cloud Platform because they have a tool which is Tackle, which is awesome to automate the process for you. It will run like in an interactive command for you where you just input what you want and it will be configured. To run Tackle, you need to install Bazel, which is some kind of makefile or make tool, but developed by Google again. And that's it. You have your Prow instance running in Google Cloud Platform. However, you also may have your Kubernetes cluster on bare metal or other hostings like AWS or Azure. So in this case, you will have to create your role-based access control policies and secrets for the GitHub tokens and some other deployments. And you need to apply the manifest for each one of the components that are in the architecture of Prow. However, you have these starters manifest that are all-in-one files, and it will also set up Google Storage or Minion for S3 in AWS if you want that. So now that you have your Prow instance running, of course, you want to build something. In this case, you just need to edit a file in the repository, which is the config.yaml. The definitions for a Prow job is quite simple. You have 3 types of Prow jobs, which are pre-submit, which are intended to run before a merge. That is when you open a PR. A post-submit, which is a Prow job running after the merge. Those are very useful for deployments or to deploy some package to Docker Hub or whatever. And also you have the periodic Prow jobs, which are run in a schedule like a cron job. So the definition is very simple. You just need to put the repository you want to observe, which is Kubernetes community in this case. Also, you need to set up the branches that you are listening to. And the specification in the spec section, you need to put place a valid pod specifications, which is the containers that will run your build. Of course, you need to launch the command that you want to test in your jobs. So in this config.yaml, you can also configure the basic behavior for every single component that we've mentioned before. You can enable and disable plugins. You can adjust the timeout for processes, and whatever you need. Whenever you are finished editing this file, you just run make update config, and the change will be deployed to your Kubernetes cluster. Now, as we just want a fully GitOps system, if you have I believe it's called autoconfig plugin. Autoconfig plugin is a plugin which is listening to changes on the config.yaml in the GitHub repository. So whenever you commit to that file, it will update automatically without the make update config command, which is awesome. Also, you may be wondering if you can do like in Jenkins, where you have Jenkins files for in-repo configuration, and yes, you do. For that, you just need to enable this in-repo config feature in the config.yaml that we've seen before. And if you do that, per each repository that you want to observe with Prow, you just need to create a .file, which is .prow.yaml, and there you place every configuration for your Prow jobs. So that's it. I think we have some time for Q&A now.
Awesome, Victor. Thank you very much for this presentation. I think is really, really cool. Actually, today and now, since your presentation, I know what is behind the scenes of the /mail to put a cat over there, which is really, really cool. Let's take a look to the questions that we have. So from Alberto Carrasco, we have a question. Is it possible to use it in Bitbucket? I think you already answered that question, right?
You can't implement this feature, this Prow system with Bitbucket. There are open issues to implement maybe in the future with Bitbucket and other providers, but at the moment there are no implementations of this.
Mm-hmm. Okay, let's take a look to see if there are more questions. In the meantime, of course, I have questions. I always have questions for you guys. Yeah, you mentioned how to deploy and so on. Do you know if there is some kind of Helm chart or something like more homemade? No, just cooked?
They specifically told that they don't have Helm chart and they don't intend to implement it in the future. Okay. So you just have the tackle feature in the repository, so you can install it. But again, it's only for Google Cloud Platform. If not, you may use the manifest.
So this is really, really specific to Google Cloud and GitHub, right? Well,
of course for GitHub and Google Cloud, but I mean, it's a Kubernetes intended system. So if Kubernetes hosts its system in Google Cloud Platform, they want it to only work with it mainly.
Yeah. I see. Have you ever? I mean, did you put in place this Prow at some point in your? I don't know if in your company or by yourself. If you did, how complicated it is? I mean, I'm asking your feeling about. Is it complicated? Is it like very hard? Is well documented or not?
It's very well documented. Indeed, each single process is well documented. If you intend to run this in production, it's very easy with the manifest. It's quite plain and simple. The only difference is that you just need to generate an SSL certificate for your ingress, and you're good to go. If you are running in local for development and testing, this tool that I mentioned, which is Bazel, allows you to run only specific components of the architecture. So it's very good for low-end PCs.
Okay.
For development purposes, obviously.
Okay, cool. Okay, let's see. Today we are a bit shy. That's okay. Angel, I don't know if you have any question.
No questions for me.
Cool. Good. I believe that, Angel, I think I mentioned this before, but looking to this, I think we should have make a feature request to the platform that we're using, because I would love to do this ChatOps to display cats or something.
Actually, if you do that feature request, a Prow job will be built.
Oh,
because
cool.
Cloud Native use Prow.
Cool. Good to know. Okay, awesome. Thank you very much, Victor, again. Thank you very much. I think it was awesome presentation. Thank you.
Thank you, Victor. Thanks.
Cool. So now we have Rafael. Rafael, the stage is yours.
Hey, hello. Thank you, Marcos. Hello, everyone. It's a pleasure to be here. And I'm Rafael. I'm from Krakow, and my talk is titled Architectural Caching Patterns for Kubernetes. But first, just a reminder, a few words about myself. I work with Hazelcast. Before I worked at Google and CERN. I'm also an author of the book. And from time to time, I do trainings and conference speaking, but on a daily basis, I do development. So I'm like most people, coding every day. That's my job. A few words about Hazelcast. So Hazelcast is a distributed company. We produce open source software. We have around more than 100 employees in total, but engineering is not that big. It's about 40, 50 people in total. And our products are, you may know us from Hazelcast IMDG, which stands for In-Memory Data Grid. We also have Hazelcast Jet, which is a library for stream processing, and Hazelcast Cloud, which is service, Hazelcast as a service. If you want to play with Hazelcast Cloud, you can go to the cloud hazelcast.com and just play with the free tier. Our agenda for today is pretty simple. There will be a short introduction about caching in a microservice world, and then we will walk through all possible caching patterns, all possible caching topologies that you can use in your system. While I'll be talking, I would like you to focus on two things. The first thing is which of this pattern you use for caching in your system, because for sure you use caching at some point in your system. And this list is complete, so there is no other pattern than this, what I will cover. And the second question I would like you to think about is, would it make sense for my system to change to any other pattern? So does any other pattern make more sense in my case? And with these questions, I leave you to listen to this talk. So let's start with the introduction. So like every system you run currently on Kubernetes, basically everywhere it's microservice. It's already like people even if it's nowadays, that's the way you build systems. And microservice world is like it's complex in terms of the architecture, because usually you have a lot of services. Services are in different versions, and they can be written in different programming languages. They use each other. So there is a lot of things happening. Another question for this talk is, if you see a diagram like this, where is the right place to put your cache? Is it inside of each service, or as a separate cache server, as a separate entity on this diagram? Or maybe it's in front of each service. And that's what this talk will be about. So starting from the simplest possible solution is embedded cache. Embedded cache means we use cache as a library and we just put it inside our application. So our diagram will look as follows. A request goes to our system. It goes to the Kubernetes service, which forwards the request to one of the Kubernetes pod. In this pod, it's the application, our business logic, our service that receives the request. And now in the application code, we check, okay, have I already executed such a request? Check it in the cache, which is inside our application. If yes, return the cache value. If no, do some long-lasting business processing, put the value into the cache and return the response. So the idea here is super simple. It's so simple that if you want, you could even write it on your own. Like if you happen to use Java, that could be your code. So we have a concurrent hash map. We have a simple function. Request goes to the function. We check if the cache contains such a request. If yes, return the cache value. If no, execute process, put it into cache, and return the response. So you can implement it on your own, but you better not do it. Because Java collection, or any collection actually in any programming language, is not good as a cache. It's not good because it misses a lot of features mentioned here on the slide. So you're better off not start reinventing the wheel. You're way better off using some caching library. If we stick to Java, a very good caching library is a Guava cache developed at Google. So where you can define all these missing features when you build your cache. Another good solution is EHCache. You will find many more like Caffeine, or just there are many caching libraries for any programming language. Now we can move this caching idea one level higher and put it not as a library but into application framework. And the most popular application framework for Java is obviously Spring. So if you happen to use Spring, that will be how you will do caching for your service. So you just add cacheable annotation with the cache name, and then every call to this method will first check if the given ISBN is found in the cache? If yes, return the cache value. Only if the value is not found in the cache, execute a method find book in a slow source. However, be careful, because for some reason, Spring by default, they use concurrent hash map. That is why you should change it. The first thing you can change is your caching manager to, for example, to use Guava. So we covered the embedded cache. It's super simple. Now there's one problem with embedded cache. Imagine that a request goes to our system, and first it's load balanced to the application on the top. We do some long-lasting business logic, put the value into the cache, return the response, everything is good. Now the same request can go to our system, and this time it's forwarded to the application at the bottom. And now what happens? We need to do this business logic once again, because these two caches, they are completely separate. So they don't know about each other. That is why one of the improvement of embedded cache would be to use distributed embedded cache. So distributed embedded cache, it's still the same pattern, it's still the same topology, but this time we'll use a different library for caching. We can use Hazelcast, which is a distributed cache. Hazelcast is still a library, so there is nothing really changes now in diagram. The only change is that now every cache from every application, they all form one consistent caching layer. So no matter to which application goes the request, they will use the same distributed cache. How to use it inside your application? So if we stick to this Spring example, all you have to do is just change cache manager, saying, I would like to use Hazelcast cache manager, and that's basically it. That's all you have to do. Now, one of the things in the distributed systems is how to, let me go one slide before, like these two caches, they need to discover themselves to form this cluster. And we thought how to make the discovery easy. If you run it on your laptop, for example, we just use the default discovery, which is multicast. But in a cloud environment in Kubernetes, it's not possible. That is why we actually created a lot of discovery plugins, and you will just use different plugins for different environments. And this plugin will use the API, for example, for Kubernetes, we'll use Kubernetes API to discover other members. So you don't even have to think about it. They will form one cluster, one consistent caching cluster. If you are interested in more details, we have a documentation. We also publish a lot of blog posts how to do it. Now, so that is it. That is embedded cache and embedded distributed cache. So let's look at the pros and cons of such solution. So from the good sides, the embedded cache is very simple to configure because you don't have to really maintain it. It goes together with the application. You have very low latency data access because the cache is together with the application. And usually you don't need any ops team needed or DevOps effort because it goes together with the application. From the downsides, you don't have control over your cache so much over your cache server because it scales up, down together with your application. It's also limited to your language of choice. For example, for Hazelcast, you will be limited to JVM-based applications because Hazelcast itself is written in Java. From the downsides, also data is collocated with your application, which is maybe not such a big problem, but we found that for big enterprises, it is actually a problem. They want to have data separated from the applications. We covered the embedded cache, the simplest one. So the next one is client server. Client server is kind of the database style. So you set up your cache server and then applications connects to this server. And the diagram looks as follows. So again, we go request goes to the Kubernetes service, it's forwarded to one of the Kubernetes pod and to the application. And now application uses cache client to connect to the cache server, which is deployed completely separately. In case of Kubernetes, it will be deployed usually as a stateful set, because cache, after all, is something that has a state. Now, if you look at this diagram and compare it to the embedded caching, there are two main differences between these two diagrams. One is obvious. This is this part. We have something new on our diagram, and this something new, it requires some maintenance. It requires basically some DevOps effort. In a big enterprise, it will always be a separate team actually managing all the servers, etc. But there's also a second difference between this client server and embedded if you look at this diagram. And the second thing is this part. So now the application uses cache client to connect to the cache server, and there is a well-defined protocol between cache and the client. That is why you are no longer limited to the same language in which your application is written. In the case of Hazelcast, your application doesn't need to be written in Java or anything JVM based. It can be written in Go or C++ or whatever you like, whatever you basically like, any language you like. And that is a very common thing, because in this microservice world, we write basically in any program. We select the programming language that is a fit for our business logic in our application. That is why it's a very good strategy. So usually you deploy your cache clusters, usually by a separate team, and then you have your applications written in different programming language which connects to these clusters. That is such a common approach that for many caching solutions like Redis or Memcache, that's the only way you can do, actually. You always set up a cache server and use a client to connect into it. Because like Redis is written, I guess, in C, so you cannot just embed it in any meaningful way. How to set up, if we stick to this Hazelcast example, how to set it up in Kubernetes. So we provide a Helm chart. We also provide an operator. Actually, the simplest way is just to use the Helm chart, Helm install, Hazelcast, and you have your caching server deployed. For the client part, I told you we use this discovery plugins, so you can just define your cache saying in the configuration, okay, use Kubernetes plugin. So get Kubernetes config, set enable true. That's it. Your client will use Kubernetes plugin to discover your server. No static configuration needed. So it is very, very simple actually to use. So we covered like the client server, and if you look at the diagram again, you see like this. I told you that this server part, from what we see from our customers, they have a separate ops team which maintains the cache server. So if it's a separate team, we could actually go one step further and put this cache not in a separate part of our organization, but outside of our organization, so put it into the cloud. So cloud is kind of a client server, but it's super specific because your server part is not maintained inside your organization. The diagram looks as follows. It's like, as I told you, the same as client server. The idea is the same. Application uses cache clients. This is still the same, but your server is deployed and maintained by some other organization, so you don't need to do any of this ops effort. You have to pay for the cloud provider, but after all, people move to cloud because it's cheaper and simpler to cloud solutions are simpler to use and cheaper after all. So how does it look like the Hazelcast configuration? If you'd like to set up the cluster, you go to this cloud hazelcast.com. You can, some clusters you can even create for free. You deploy the cluster in the console like in AWS. And then your client configuration looks like this. So you basically get a token from your web console or your CLI and put it into your application, and that's it. The application will automatically connect into your cluster. And the discovery token idea is not only Hazelcast. We didn't invent it in Hazelcast. Actually, in most cloud solution like MongoDB or whatever, you will find this way. You just click on the console, create your database cluster, whatever, get the discovery token, put it into your application, and your application will find your server part. Short summary about client server and cloud caching. So from the good sides, data is separated from the application. We have separate management. So if you need to suddenly scale up your cache server from 3 nodes to 20 nodes, it's very simple. It's programming language agnostic because we use cache client to connect, and there is a well-defined protocol between your client and server. From the downsides, you usually need a separate ops effort, or you need to pay for the cloud. Latency is higher. It's not necessarily higher, but you have to think more about latency. Because if you deploy your on-premises cache server, you'd better make sure that it's in the same local network than that your application is located in. Because the caching is, caching is a domain of very low latency. You use caching to have very low latency data access. That is the reason why you use caching. That is why you need to deploy your cache server in the same, even one router hop is a lot. If you use the cloud solution, we also had to think a lot about how to make it, low latency. And obviously, when you create your cache in the cloud, cache server in the cloud, you need to specify the same region where your application is located in. But also, we don't provide the infrastructure. We will deploy your cache server on your cloud provider of choice. So you can choose from AWS, GCP, or Azure. And you should choose the same where your application is located in. But that's not all. We also provide a way to do a VPC peering. So your virtual network of your application will be the same, will be peered with the VPC in which we created a cache server for you. So there is not even one router hop in between your application and the cache server. And that is very important because, as I said, we are in the low latency domain. That is in-memory data computing. That is the low latency domain. Okay, we covered I would say, classic topologies. So you may say, okay, we've heard a lot about embedded client server. It's nothing new. So now there will be something new. So cache as a sidecar. It is something new because Sidecar it came together with the container orchestration frame systems, and it's very popular thanks to Kubernetes actually. So your deployment, it goes like this. So again, request goes to our system. It's load balanced to one of the Kubernetes pod. And now in one Kubernetes pod, we have 2 containers. So one is our application container, as always, our application business logic. But we also deploy a second container, which is a cache server. And obviously, all cache containers from all the pod replicas, they form one consistent caching cluster. And now the application uses cache client to connect to the cache container, to the cache server. So, this solution is somehow similar to embedded mode, somehow similar to the client server. So it will be similar to embedded because your cache and your application is located on the same physical machine, because Kubernetes guarantees that that all containers in the same pod are located on the same physical machine. So they are scaled up and down together because Kubernetes scales up and down pods, not containers. And there is no discovery needed because your cache server is always located on the local host because containers share the networking in the same pod. However, this solution is also similar to client server because after all, your application uses cache client to connect to the cache server. So your application can be written in any programming language and connect to your cache. So there is no problem with that. How to deploy something like that? So to deploy it, we provide a static cache configuration. So we add, always connect to the local host default port because your configuration is static for your application, but after all, the overall configuration is dynamic. You just know that your cache server will be always located on the local host. Your Kubernetes configuration will look like that. So you will have 2 containers in one pod. One will be your application business logic, and the second one will be your cache server. As simple as that. Pros and cons of cache as a sidecar. So the configuration is very simple. It's programming language agnostic. We have low latency, and there is some isolation between data and application. It's on the container level. From the downsides, we again don't have flexible management because your cache will scale up and down together with your application, and the data is co-located with the application pod. The last caching pattern will be something completely different. It will be reverse proxy caching. It will be something completely different because so far in all these topologies, application was always aware that such a thing as a cache exists. So application it was explicitly connected to the cache. Now we will do something different. We will put cache in front of the application, so the application will not be even aware that such a thing as a caching exists. Diagram looks as follows. So request goes to our system, and just before a Kubernetes service, or it can be even if you use you can even put it inside your ingress controllers. Ingress controller is based on Nginx. You have your caching layer, and so if request is found in the cache, it's not even forwarded to the application. And for this, Nginx is a very good solution, no matter if you use Kubernetes or not, but Nginx is a very mature solution. It's also very well integrated, as you probably know, Kubernetes uses Nginx internally. This is the Nginx configuration for caching. So you add this configuration, and you have a caching layer together with your Nginx. Nginx is good, but it has some, maybe not problems, but some characteristics that could be improved. So it's only for HTTP, which is usually not a problem, but it's not distributed and it's not highly available, which can be a problem. And data, it's not actually stored on the disk, but it can be offloaded to the disk, which is, for example, different in case of Hazelcast when you are guaranteed that your data is in memory. That is why you are guaranteed about the latency. One of the variants of the reverse proxy caching is if we combine it together with the Sidecar, and we create our last variant for today, which is reverse proxy Sidecar caching, which will be putting cache as a Sidecar container. So this time it will go as follows. Request goes to a Kubernetes service, is forwarded to the Kubernetes pods. But this time, it's not the application container that receives the request, but it is something called reverse proxy cache container. So it's kind of interceptor of all the traffic which goes to the application. And if the value is found inside this reverse proxy cache container, It's not even forwarded to the application. Now, if you think about this, in general, about this reverse proxy idea, that application is not aware of the caching, there are some good things about it and some bad things. So let's start from the good things. So why would you use this reverse proxy? Why application should not be aware of caching? So you remember this diagram. I've started the presentation from this diagram. A lot of services in different versions, written in different programming languages, they use each other. Normally, this is a small diagram. Usually you have way bigger. Now you can look at this diagram, do some measurements, and you can say, without modifying any of the services, you can say in a declarative manner, changing only the configuration, I would like to have cache in these two services. And that is the whole beauty of the reverse proxy caching. That you can, in a declarative manner, add caching layer to your system. That is how it will look like in your Kubernetes code. So you need, maybe starting this time from the bottom, you need obviously two containers. One will be your application, another will be the cache, this interceptor, which will go to the caching. And you also need some init networking container, which will change your IP tables of your pod so that the request doesn't go to the application, but it goes to the caching proxy container. Now, if you look at this diagram again, it may look similar to something called Istio, so service mesh, because that is exactly the idea of Istio. I mean, that is what Istio does. It has this envoy proxy deployed as a sidecar, and now every request is intercept. Every call to your pod is like intercepted, and Istio is basically for security and traffic management. But recently they implemented a long-lasting feature, which is caching. So you will be able soon to use caching. They recently closed this issue. Use caching together with Istio, and then that will be a first reverse proxy sidecar caching, first major solution for reverse proxy sidecar caching. But this whole idea that application is not aware of caching, it also has some drawbacks. So if you think about it, like what is the biggest problem with caching in general, everyone will tell you the same. Like the hardest part of the caching is cache invalidation. Meaning when to decide that your cached value is already stale, that it's outdated. I should not use the cached value, but I should go for the logic. And if your application is aware of the caching, you can add some business logic. I would like to evict this value, or I would like to. You can have a control over this. But if you use reverse proxy caching, you're basically up to some HTTP configuration, which is basically timeouts, ETAGs, basically timeouts. So that will be the biggest problem of reverse proxy caching. So short summary about reverse proxy and reverse proxy sidecar caching. So the good thing, the main reason why we'll use it, it is configuration based. So that is the whole beauty of this. It's programming language agnostic, it's everything agnostic, and it is very consistent with the containers and microservice world. So I think soon it will be very, very widely used. From the downsides, I mentioned already cache invalidation, but other downside is there is for the reverse proxy sidecar, there's no major solution yet. It is Istio. You can use it with Istio, but there is also not very, very like well tested on production. So it's reverse proxy itself. You can Nginx. You can use Nginx is very major, but all the reverse proxy sidecar it is not yet in this phase. So like this, we covered all caching patterns, all caching topologies that you can use in your system. So as a short summary, what I propose, I will try not to repeat anything I said before, but what I propose as a short summary is a simplified, maybe oversimplified decision tree, which can help you find your perfect cache for your system. So the first question I would ask if I were to choose which caching solutions for me is, does my application need to be aware of the caching? If no, am I early adopter? If no, use reverse proxy with Nginx. If yes, use reverse proxy sidecar caching. Now, if your application needs to be aware of caching, then the next question is, do I have a lot of data or security restrictions? Basically, do I work in a big organization? If no, does it need to be language agnostic? If no, use embedded or embedded distributed cache. If yes, use Sidecar. Now, if you have a lot of data, security restriction, working in a big organization, then the last question you need to ask is my deployment cloud? And now, if not, use client server on premises. If yes, use caching as a service. And with this last slide, I would like to, so this is basically the oversimplified decision tree, but it can give you at least some guidance where to look for. Now, as a last slide for this presentation, I've shared some resources. So the first one is our blog post about using Hazelcast as a sidecar container. Second one is our prototype with reverse proxy sidecar caching. Third one is it's not related to this talk, but it's a very good blog post about caching in general. And the last resource is a very good video about a very good presentation about using Nginx as a reverse proxy caching. And with this last slide, I would like to thank you for listening, and it was a pleasure to speak here. And let me check if there are any questions.
Thank you very much, Rafael. I mean, amazing talk. Really good. I was taking notes, actually. It blows my mind, some of the patterns that you put in place. I was more, used to the typical ones that you mentioned before. And actually, we have some questions from the audience. So, Player Lartategi is asking, in the case of Sidecar cache, could the cache compromise the pod stability in terms of resources, like, for example, memory, CPU, something like that?
Yes, and it would be the same with embedded mode. That then you have to think about either to set up. I mean, usually what you will do, you will set a good eviction policy so that it will not blow up your pod. Or imagine that you use Sidecar embedded mode and you have too many things in the cache. You don't want your application to fail. That is why you have to be careful. But if you use it, if you use it just for caching, usually setting up good eviction policy is good enough. If you use it for really an in-memory database, then you will usually not set it up as an embedded, because then you don't want to evict your data.
Okay, cool. Because I guess also since you put this cache as a sidecar, I'm pretty sure it's also a bit, I don't want to say complicated, but tricky to put the right resources in the YAML file for the Kubernetes and so on, right?
Yes, exactly. Yeah.
Cool. Okay. Also, we have another question from Alberto Carrasco. Do you usually work with other frameworks similar to Spring, such as Micronaut? If so, what is your experience in combination with Hazelcast?
So yes, I mean, Hazelcast is integrated well with Java frameworks, like obviously Spring. It is #1, but with the now Micronaut and Quarkus, they are getting more popular because of this native images, etc. So we're integrated with Quarkus. We provide a Quarkus extension, and for Micronaut the same. We are one of the cache provider. If you use Micronaut cache module, you can choose Hazelcast. So yes, it's well integrated.
Cool. Okay, let me see if we have more questions in the general side or something. Yeah, Pelayo Lartategi mentions, in my experience, Hazelcast works great with Micronaut, so good feedback over there.
Good to hear that. I will pass it to my colleague who implemented this integration. We actually had today we had a discussion about like what would be the next step in the Micronaut integration. But happy to hear that.
That's cool. That's super nice. Yeah, I don't know if there is more question. I could have another one. For example, I was curious about this reverse proxy. I think you did a very good summarize at the end with the flow of based on question, what is the best strategy for you. In terms of, for example, TLS, is there any restriction in the patterns in the way that, okay, if you want to apply this pattern, TLS doesn't fit or is not needed or is not possible to make it?
I think if you configure this correctly, I think it is possible to make it. So I don't see any problems in the reverse in this reverse proxy caching. I think it will work. But yeah, I think the most problem is that actually, as I mentioned, like that. I think I really actually believe in this reverse proxy. I really think this will be the future. Especially for like I think the Istio will change the thing because people are using Istio. It's very popular, and they already use it on production. So they will use also this caching feature. It's basically caching is a feature of Istio now. So it's like I think it will be well used. So I don't think you will have any like other problems than what I mentioned.
Cool. Actually, when you mentioned that. It came to my mind like a wording like cache mesh instead of service mesh, but
yeah,
it's really interesting topic.
Yeah.
Cool. Okay, let me review because we are running out of time. I think that's all in terms of questions. So I think we can make the closure of this session. Let me just share super fast my screen. So yeah, I just want to tell you, everybody, thank you very much for coming along. For all the attendees, thank you for your attention, for your questions. And also I want to thank you, Rafael. I want to thank you, Victor, for invest your time on this. I really see a lot of very interesting topics in this. Actually, I would have more questions for you, but we are running out of time. And yeah, thank you very much for coming on, and I hope you come back at some point. Cool.
It was a pleasure.
Awesome.
Yep. Thank you very much,
cool.
Victor. Great to very nice talks, and thanks everybody on the event. We'll come back soon on with more interesting talks. And that will be on February. So stay tuned, and we will be letting you know, guys, what's coming up next. And please don't forget, if you have something interesting to share with this audience, with our network, please submit your proposals, and we'll digest. But again, thank you very much, everyone. Thank you, guys.
Cool. See you guys. Ciao.
Bye-bye. Bye.